Dear students, let's proceed with our lectures and let's finish this part of lecture on the topic of considering the so-called distributed lines, distributed line circuits with distributed parameters. At application to them, rather high electromagnetic fields with rather high frequencies. And here we consider totality of infinitesimal elements consisting of connected in series inductance and resistance, and connected in parallel capacitance and parameter G0, which correspond to leakage current through insulation between these two lines. And at writing down second Kirchhoff's law for such a branch and first Kirchhoff's law for current here, we can write down the so-called telegraph equations, which connect currents and voltages with specific parameters of such a line. Specific parameters, it's L0, R0, C0, G0. It's equal to ratio between real inductance, resistance, capacitance, and G over length of the line. Then we have been considered application to this line of sinusoidal voltages currents, and we have been considered steady-state processes when we can use complex variable method, and when we can replace instantaneous values like here, small letters, by their phasors. And in such a case, we can transact from partial differential equation to equations which depends only on coordinate, only of x, and in such a case we are able to get solutions for voltages and for currents through the so-called secondary parameters, its characteristic impedance and its propagation coefficient gamma, which consists of real part, it is attenuation coefficient, and from imaginary part it is phase coefficient. To determine this integration constant, we should assign either voltage drops and currents at the beginning of the line, U1 and I1, or voltage drops currents at the end of the line at U2 and I2. And we consider parameter from the end of the line. So x is distance from of infinitesimal point, infinitesimal element from the end of the line, and we will assign U2 and I2 its voltage drop and current at the end of the line. And knowing, substituting here x equal to 0, and at x equal to 0, u equal to u2, and at I equal to I2, we can determine this integration constant, and we can get expressions both for voltage drop and for current through levels of voltage drop and current at the end of this long line. And remember that x here is distance from the end of the line. Then we have here exponential function with plus power and minus power, and we can express them through hyperbolic function. It's hyperbolic sinus. I would like to remind you this material from mathematics. Hyperbolic cosine equal to 1/2 of e in the degree gamma x plus e in the degree minus gamma x, and hyperbolic sine is 1/2 of e in the degree gamma x minus e in the degree minus gamma x. And we can rewrite this expression through hyperbolic function. How? You see, we have here in the degree gamma x, we have and in the degree minus gamma x, and we can rewrite it will be u2 multiplied by in the degree gamma x 1/2 plus 1/2 u2 is the degree minus gamma x, and u2 1/2 u2 may be written before brackets, and at brackets it will be in the degree gamma x plus into e in the degree minus gamma x, and such an expression equal to hyperbolic cosine of gamma x. So we replace these two summands by u2 multiplied by cosine gamma x, and then you see this item and this item, they have the same common factor zci2, and in brackets it will be zci2 over 2, and the brackets will be in the degree gamma x minus in the degree minus gamma x, and it's equal to sine, hyperbolic sine of gamma x, hyperbolic sine of gamma x with this coefficient. It's for u, and then for I the same. We have I2 and I2 over 2 here, and in brackets it will be e to the gamma x plus e to the minus gamma x. So it is hyperbolic cosine gamma x, okay? Then coefficient u2 over zc, and here u2 over zc over 2, and in brackets it will be e to the gamma x minus e to the minus gamma x, and it is sine gamma x with this coefficient, okay? And this 1 2 is we have here 1 2 and we have here 1 2, so it will be just sine hyperbolic sinus and hyperbolic cosine. So here we can see that currents and voltages at any point are functions not on x coordinate but on frequency, because propagation coefficient gamma depends, you see, depends on frequency, and here both real, its real part, and imaginary part, its attenuation coefficient and phase coefficient will depend on frequency also. And it means then if we have voltage and currents waveforms of complicated shapes with different as sum of different harmonics with different frequencies, when such waves are transmitted through such lines, and attenuation coefficient will be different for different harmonic with different omegas, substantial distortion can take place, and to avoid this distortion, line parameters should comply such conditions. See, R0 over L0 equal to G0 over C0. I will show you why it is in such a way. Let's write down propagation. Let's write down propagation coefficient. This expression. Let's write down it. Its designation of propagation coefficient. Gamma power 2 was equal to product of this expression of this in brackets, but gamma is square root from this product. Here we can rearrange this equation. We can put coefficient L0 C0 before brackets, and in brackets it will be G0 over C0. You see, because we have here you see it is G0 over C0 plus J omega, and C0 will vanish, C0 and this C0 will they will be cancelled. It will be just J omega. If you multiply this L0 C0 by J omega, you will have L0, like here you will have here you will if you substitute this by C0, it will be j omega C0, and if you multiply this expression by C0, it will be just G0 like here. So we multiply and divide this expression by C0 and multiply and divide this expression by L0. So if we divide both sides of this expression bracket by L0, it will be R0 over L0 here, and here it will be just J omega, yes? And so we put before these brackets C0, and before these brackets we put L0. So we have such an expression. Then we can write this expression as product of square root from L0 C0, and in brackets it will be, if we used such condition, R0 L0 over R0 over L0 equal to G0 over C0, this expression in brackets will be the same. Let's consider that R0 L0 equal to G0 over C0. So this will be this expression in brackets will be equal to this expression in brackets, and so it will be under square root, it will be this expression power 2, and we can write it just without square root from expression power 2, it will be just this expression. So it will be square root from L0 C0 multiplied by this expression, because if condition R0 L0 equal to G0 C0 is fulfilled. Okay, so we have such an expression, and we can write it as sum of real part, this real part at this condition, and this imaginary part j omega multiplied by square root from L0 C0. So we can present it. You see here we have C0 power 2 in denominator and C0 in numerator. So we can write down that it will be and L0, if we use this condition, this expression may be rewritten in such a form. You see, we will have L0 over C0, L0. If we substitute, you see, it's we may substitute L0 as G0 C0, this L0 equal to R0 over G0 and multiplied by C0. If we substitute it here, instead of this L0, we will have R0 C0 over C0 power 2, it will be just C0, and then we can rearrange it. It will be just this R0 under square root, yes, and it will be G0 in the first degree, because this G0 and G0 will be cancelled, okay, and this C0 power 2 will be cancelled with this C0. So we will have only square root from R0 G0 under the square root, yes, and it will be j omega square root from L0 C0, okay, and this real part is called attenuation coefficient. You see, it is was attenuation coefficient alpha, and this second imaginary part is called phase coefficient. Is called phase coefficient. So we can write down that attenuation coefficient equal to this square root from R0 G0, and it does not depend on frequency. And here phase coefficient equal to square root from L0 C0, it will not depend, or it does not depend on frequency also. So in such a case, if attenuation coefficient does not depend on frequency, line with all frequencies will propagate through such a transmission line without distortion. So such a line is called distortionless line. And in such a case, not only attenuation coefficient, but also characteristic impedance will not depend on frequency. Why? We can substitute its designation of characteristic impedance. Yes, we can substitute here this condition, and rearranging this equation, we will have such an expression, and as R0 over L0 equal, like here, R0 over L0 equal to G0, G0 over C0, it will be equal equal expression in numerator and denominator, and they may be cancelled, and we will have only square root from L0, C0, and it's equal to rho. So in distortional line, we've got such, I've told you that it will be square root from L over C, its characteristic impedance, it will be used many times in the future and in our past lectures also. So it is the end of this lecture. Let's meet next time. Bye bye for now.